So we proved this Matula theorem. What is the statement? Here. And somebody could have a question that why do we consider C sub r minus 1, which is edge connectivity instead of vertex connectivity. But we know that its edge connectivity is smaller than or equal to r, then its vertex connectivity is also smaller than or equal to r. So this is more restrictive, class of graphs. So this is stronger concept than vertex connectivity. So if you consider just coloring with the same condition, but instead of edge connectivity, if you consider vertex connectivity, same upper bounds holds. So we consider about this and this. So now we can consider about this S sub r minus 1 chromatic number. So recall that S sub r minus r is the graphs with maximum degree r. So regarding this S sub r chromatic number, Roberts in 1966 proved the following upper bound. If G is following theorem which provides an upper bound. Let G be a graph and D1 to dk be at least 0 such that summation of di is at least delta of G minus k plus 1. Then there exists a partition V1 to Vk or Vg such that in each color class the maximum degree is bounded by di for all I. So then what happened? As a corollary, we directly get this upper bound. How? We take a D1 to dkV or r minus 1 where k is the ceiling of delta of G plus 1 over r. Then what happened? The summation of di is simply k times r minus 1, which is at least delta plus 1 minus k. So this condition holds. So that means you can partition the vertices into k sets so that each induces a graph with maximum degree r minus 1. And you give the same color to each parts, then that gives us the S sub r minus 1 coloring. So this theorem implies the corollary. This theorem was proved by Roberts, and if I remember it correctly, this one was someone's conjecture. Not too long conjecture. Not too old conjecture at the time, but someone conjectured it, and Roberts proved it. And Roberts was born in 1948, so he was like 18 years old, or even earlier when he proved this. Even younger than that, because this date is when when the paper was published. Anyway, so how do we prove this? we can prove by considering some function for defined from the partition. And then by the maximality of some choice, we automatically gives what we want. Let me show you what I mean. Is that for a given partition, you want to say UK of the vertices. We define function f of u1 to uk with the summation of number of edges inside each ui over di, and you sum it up for all I between 1 and k. Then the number of such partitions are finite. So there are finitely many such partitions of the vertices of G. There must exist a partition P1 to Pk which minimize the value of f. So out of finite partition, you apply this f, then you get number. There are finitely many numbers, so you can choose the smallest one, and then you look at the partition which give you the smallest value. And then now we claim that this is our partition, our desired partition. To check that, let's say if there is some vertex in X in Vi, and we want to show that it has not too many neighbors in its own class. If X has, say, more than Di neighbors in Vi, and X has at most d sub j neighbors in some Pj. So X is here, and then it has, say, Ti plus 1 neighbors here, while it has at most Dj neighbors here. Then what we can do is we can just move it to here. And how does this change the value of f? Then moving X from Vi to Vj decrease f by more than 1. Because, so here, everything else is same except the ith term and jth term. Ith term, you lose at most this on the top, and then it's divided by di. So you lose strictly more than 1. Di plus 1 over di is strictly more than 1. And how much does it increase? And increase. So now it's here, it's moved. And then it has at most dj neighbors, meaning that at most dj edges are added. And then which is divided by dj. So increase by at most 1. Then this contradicts the minimality of this partition. We assume that this attains the minimum value of f, but we just found the better partition with a smaller value. That means, and we may assume that dj is at least dj plus 1 for all j in k. Otherwise, we can move to the j which satisfies the other way around. However, then we have degree of x is summation of, say, dj plus k tj plus 1, j is between 1 and k, and that's maximum degree plus 1, which is a contradiction. That means this doesn't happen. So every vertex x in Vi has at most di neighbors in Vi. So this contradiction proves the theorem. And then it trivially implies this corollary. So that's what we have for this S sub R minus 1 coloring. And now we consider the O sub R minus 1 coloring. So this is a coloring where you color the vertices so that each color class induces a graph with bounded component size. Remember that if you consider S1, that means maximum degree 1, which means matchings and isolated vertices. So which is same as O1. O1 means that each component has size at most 2. So if you apply that to this corollary, then you get delta plus 1, delta of g plus 1 over 2, and upper bound. So this provides an upper bound for all coloring. And what about for larger R? So that's what we will learn next time. Next time we will discuss about some bounds on this component coloring. And we will also learn about, other theorems. Yeah, thank you.